Welcome to the course Business Analytics and Data Mining Modeling using R. So, in this particular lecture, we will start our discussion on logistic regression. So, let's start our discussion. So, logistic regression, they are equivalent of linear regression technique that we have gone through in previous lectures for categorical outcome variable. So, linear regression that we have discussed before, that was mainly for the numeric outcome variable, continuous outcome variable. Now, logistic regression is an equivalent technique for categorical outcome variable. So, typically as you would understand that linear regression is typically used for the prediction task, and a logistic regression is typically used for the classification task. However, though the categorical outcome variable we use, the predictors can be categorical or continuous. So, let us understand more about logistic regression. So, typically applied in a following task. Classification task is one where we predict the class of a new observation. So, that is the first category. Then this particular technique could also be used for profiling, for example understanding similarities and differences among groups, right. So, classification task and profiling, though the way modeling is done, there is not much difference. So, in terms of modeling, these steps for both these tasks, classification or profiling, not much is going to change. However, the ideas, the objectives are different. So, classification task, we would like to predict the class of a new observation. In the profiling, we would like to understand similarities and differences among groups. So, let us move forward. So, what are steps for logistic regression? So, first in logistic regression, because this is typically for classification task, we estimate probabilities of class membership. So, if it is a M class scenario, so probably we would like to estimate probabilities of belonging to class 1 to class 2 and up to class M. If it is a 2 class scenario, we would like to estimate the probabilities of a new observation belonging to a particular observation belonging to class 1 and class 0, right. So, therefore, with this so that becomes the first step. So, first we would like to estimate these probabilities, so probabilities of class membership. Then the second step is about classifying observations using these estimated probabilities value, right. So, as we have discussed for other techniques, so first one is typically the most probable class method, wherein we look at all the estimated probabilities of class membership, and we assign the observation to the class with highest probability value. So, that is the typical scenario where we are looking for overall misclassification error. We are looking to minimize overall misclassification error, and we do not have any specific class of interest. So, this is the typical method that we follow, right. This particular most probable class method is equivalent for a 2 class case, the cutoff value of 0.5 is equivalent to this most probable class method. So, if we have just 2 classes and we want to apply most probable class method, we are just looking to minimize overall misclassification error. In that situation, the 2 class scenario, if because if the probability of a record belonging to class 1 is let us say P, then probability of that particular record belonging to class 0 is going to be 1 minus P. So, therefore, 0.5 probability value of 0.5 can be used as an appropriate cutoff value for a 2 class scenario and for most probable class method. Now, as we have talked about when we discussed classification and prediction performance matrix, when we discussed different metrics for classification, we also talked about that if you have estimated probabilities values like we do in this for this particular technique, logistic regression. Then we can also use a one-way Excel tables to find out the optimized cutoff value for a particular problem, for a particular classification problem or task. So that can also be done, right. So however, that might lead to overfitting. So those things we have already discussed in that particular lecture. Now the second scenario is class of interest, wherein we have the user specified, we have to use user specified cutoff value. So in the class of interest, we might have one particular class which is a low probability event. Therefore, we would like to identify more members of that particular class. And so we have talked about different scenarios using cost based method, misclassification cost and other things in previous lecture already. Right now, for class of interest, if we are dealing with a two class case, so typically a value that is greater than average probability value for class of interest, but less than 0.5, probably that can be used. So this is just a kind of rule of thumb based on the experience in modeling. So however, depending on the probabilities value and depending on the if we have that cost matrix, we can find out a good enough cutoff value or optimized cutoff value in class of interest scenario. So these are two typical steps. First, we would like to estimate probabilities, and then these probabilities are used to classify observations. Now let's move forward. So now we will discuss more about the logistic regression model as such. So typically this particular model, so as we talked about, this is for classification task. So this particular model is typically used in cases where a structured model is preferred over data driven models, right. So we have discussed a few data driven model, right, like Neobase and KNN, right. So we have discussed a few data driven models. However, when we require a structural model, when we have some assumed functional form between the outcome variable and and the set of predictors, or we understand that there is some sort of relationship between the predictors and outcome variable, and if we are looking to structure that, we are looking to model that, then probably logistic regression is an equivalent technique for the same structural technique for classification task, just like linear regression is for prediction task. So as we understand that categorical outcome variable, if we try to model it as a linear function of predictors, so that is not possible because of various reasons. So as mentioned in second point here, categorical outcome variable cannot be directly modeled as a linear function of predictors, right, because when you have a y a categorical predictor, so you are going to have few values that are nothing but the different categories. Let's say if there are m classes, so there are going to be if we express that in numerical code format, then it is going to be 0 or 1 or 2 or 3 up to m minus 1. So those could be the classes. So now if you try to model that as a linear function of predictors, where predictors could be continuous and categorical, so that range would be minus infinite to infinite. So that there are going to be certain problems, so which are expressed. Some of these issues are expressed in this particular slide as well. Inability to apply various mathematical operators, one. So because your categorical variable could be nominal variable, so more often than not the categorical outcome variable that we might use, it could be nominal variable. So therefore we have already discussed in one of the lecture the kind of operators that can be used. So equal to and is not equal to, so these are the two operations that can be performed, and therefore that linear modeling cannot be applied. Now variable type mismatch, that is also obvious that in the outcome variable we have just that is categorical, and in the set of predictors we might have continuous and categorical variables there. So therefore interpretation and modeling and everything is mismatch there. Now, another thing to understand is range reasonability issues. For example, categorical outcome variable, as I said that the values could be one of, if we are expressing the categorical variable in numeric code format, where 0 is representing one of the class 0, then 1 class 1, and similarly class m is being represented by m minus 1. So, in that fashion you will have one of these values from 0 to m minus 1 in LHS side, that is outcome variable side, and then RHS side you would have the predictors, and therefore some of those predictors could be numeric variables as well. So, therefore the range could be minus infinite to infinite. So, therefore that range reasonability issues would also occur. So, lots of things. Very few that is just equal to and is not equal to operators can be applied. Variable type mismatch is there, range reasonability issues are there. So, because of this, categorical variable cannot be directly modeled as a linear function of predictors. So, let us move forward. So, how do we, so what we do in logistic regression model then? So, instead of using outcome variable y, which is typically which is actually the categorical variable as well. So, instead of using this categorical outcome variable y in the model, a function of y called logit is used. So, let us understand what this function is about. So, before we reach to our standard logistic regression model and discuss logit and other related concepts, let us think about modeling probability value as a linear function of predictors, specifically in a two class scenario, right. So, if we have just two class, as mentioned in the slide as well, if we are in a two class scenario, so we just need to estimate one probability value, that is probability of belonging to class 1, the other would be 1 minus of this particular probability value. So, therefore the probability value p can be expressed in this form as a linear function of predictors, beta 0 plus beta 1 x1 plus beta 2 x2 plus beta p xp, if there are p small p, that is p number of predictors. So, what is the problem with this particular formulation? So, let us discuss this. So, if we have a two class scenario and we express the probability value of class 1 membership as a set linear function of predictors, then what are going to be problem with this? So, let us look at the LHS range. Now, LHS range will improve from a set of two values, that is 0 and 1 to this range from 0 to 1, right. So, now because this is LHS is now probability, so therefore the probability value can range from 0 to 1. So, the LHS range improves from just two distinct values to a small range, that is between 0 and 1. However, it still cannot match RHS range, which is minus infinite to infinite. So, what we can do? Can we bring RHS range, that is right side range to 0 1 level? So, it is possible with some transformation. So, this is typically non-linear approach we have to take. Some non-linear transformation we would have to perform in a manner that the expression that we have on the right hand side, that linear function of predictors that we have on the right side as expressed here, in a form where it starts taking in a non-linear form, where it starts taking values from 0 to 1. So, typically as you can see in the slide, a non-linear function of this form, which is called logistic response function, can actually be used to perform this transformation. So, we can express probability value as this. Probability value p can be expressed as 1 divided by 1 plus exponential of minus of beta 0 plus beta 1 x1 plus beta 2 x2 plus up to beta p xp, that is linear function of our predictor. So, you can see from here that the RHS side, the earlier RHS side that we had, now it is it is within this exponential, this is power to the exponential, negative power to the exponential, and now irrespective of the values that is being taken by with this linear form of predictors, the value of right hand side would be in that 0 1 range. And now you would see that left hand side and right hand side both are in the same range 0 to 1, right. So left hand side is probability values, probability value in 2 class case, or in for that matter any class case, this is going to be 0 and 1, between 0 and 1, and right hand side is also now between 0 and 1. As you can see, when denominator, it this exponential function, it can range from 0 to infinite. So therefore when it is approaches 0, so the value is going to be 1. When it approaches infinite, then the value is going to be close to 0. So therefore this right hand expression is going to be in that range 0 to 1. So now once these two ranges, once range reasonability is okay, now we can move forward. The previous equation that we just saw can be rearranged in this form. So now instead of having that form, we can use this particular rearrangement, wherein we have on LHS side p divided by 1 minus p, and on the RHS side we have the exponential of beta 0 plus beta 1 x1 plus beta 2 x2 up to beta p xp. So in this particular formulation, you would see that now the range here has changed, but it is now between 0 to infinite for both the side, LHS and RHS as well. Now if we look at this particular equation in the RHS side, now this is more of a proportional form. So if we use this particular model, the interpretation would be in percentage terms, right. However, we can do a certain more transformation to bring it to typical standardized form of equivalent form of linear regression. So that being the objective, so we would like to reach to the equivalent standard formulation that we use in linear regression for the logistic regression as well. So now LHS, the expression that we see, p divided by 1 minus c, that is actually nothing but the definition of odds. So odds is another measure of class membership, where it can be defined as expressed as odds equal to p divided by 1 minus p, and it can be defined as odds of belonging to a class is defined as ratio of probability of class 1 membership to probability of class 0 membership, right. So it's a ratio of whether there is going to be success or failure. So this particular, now we can use, instead of using this expression p divided by 1 minus p, we can replace it with this odds, which is also another measure of class membership. So this particular metric odds is popular in sports, horse racing, gambling, and many other areas. Now you can also understand that the range for odds metric is from 0 to infinite. So the same point is here. In previous equation, now it can be rewritten as odds equal to exponential e to the power beta 0 plus beta 1 x1 plus beta 2 x2 up to beta p xp. So a range is now 0 to infinite. As you can see, both LHS and RHS, we have already matched these ranges, and that same thing continues. Now if we take a log on both sides of this particular equation, then what we get is log of odds, and on the right side we get a linear function of predictors that we wanted to achieve, that is beta 0 plus beta 1 x1 plus beta 2 x2 up to beta p xp. Now once we take log, now let's look at the range reasonability on let's look at the LHS side, log odds. So as we know that log of a value, that log based function, they will take range from minus infinite to infinite, and RHS is now in the linear function format. So it will also take the same range, minus infinite to infinite. So range is matching. And this particular formulation that we now see, log of odds being expressed as a function of these predictors, beta 0 linear function of these predictors, that is beta 0 plus beta 1 x1. So this is the standard logistic model. So this is a standard formulation of a logistic model. So this is the formulation that we typically used in a linear regression modeling. Now this particular term on the in the left hand side, log odds, is called logit. So as we talked about that instead of using the categorical outcome variable, we would be using logit. So this is the formulation, this is the expression for logit. So logit is nothing but log odds, which is log p divided by 1 minus p. So this particular logit is going to be used as the outcome variable in the model instead of the categorical y. Now odds and logit, as we have understood, now both these matrix can actually be written as a function of probability of class 1 membership. Right. To understand more about the relationship between these three matrix, let's see few plots in our studio. Let's open our studio. So what we'll do, we'll create some some plots for this. So odds versus probability value of class 1 membership, and also logit versus probability of class 1 membership. So we'll try to understand the range reasonability, as well as we'll understand how the values are being taken. So odds, as we talked about, odds can be expressed as p divided by 1 minus p. So this is the particular function that can be used to plot this particular mathematical relationship, where curve is the function. So first argument is the expression. So if in this case probability value, so p divided by 1 minus p. So this is the expression that we want to plot, right? So p divided by 1 minus p, the values can range from 0 to 1, right, because the probability is value. So that is the range for probability value. So the same has been specified in argument second and third. So third is from 0 to second argument is from 0, and third argument is to 1. Now type of the plot is going to be L, that is linear, linear plotting, and then this is expression, that x name, this particular argument is p, because it is the value of p that we are changing from 0 to 1. So a label for x-axis is going to be probability of success, because this particular these particular values are probability of class 1 membership, and the label for y-axis is odds. So let's execute this particular code, and we would see a plot here. So let's zoom in. Now you would see that on x-axis we have the values ranging from 0 to 1, and on y-axis we have the values ranging from 0 to infinite. However, we are just showing up to 0 to 100. So on y-axis we have odds. So we can see as the values increase from left to right on x-axis, from 0 to 1, the value of odds keeps on increasing, right. So this particular odds value will keep on increasing. So as we approach, as you can see 0.8, so this up to this point there is sharp increase in the odds values, and when we reach on x-axis, when we reach to 1, the odds value on a y-axis it reaches to infinite. So this is the plot for odds. So if we are talking about typical default cutoff value that we use is 0.5, then the corresponding odds value is going to be somewhere around this particular 0.5 value. So the corresponding odds value is going to be 1, right. So let's move forward. So similarly we can generate a plot for logit versus p, that is probability of class 1. So logit can be expressed as log odds, and which is nothing but log p divided by 1 minus p. So same thing we can express in the this particular function curve, where first argument is going to be log p divided by 1 minus p. Second and third arguments are going to be remain same from 0 to 1, because probability values will range from 0 to 1. Type of plot is again L. Name of this argument, name of x is p, because p is the variable that we have, and this is styling detail. Then we have appropriately we have specified the labels for x-axis and y-axis. Let's create this plot as well. So let's also create x-axis. You can see in the curve function we have last argument is x-axt as n. That means x-axis was not plotted. Now we'll create x-axis separately. Let's do this. Now let's zoom into the plot. Now from here you can see the values along x-axis range from 0 to 1 for this particular plot, and you would see that on y-axis we have logit and the values range from minus infinite to infinite. However, for this particular plot we see typically the values from minus 4 to 4. Now as we move from left to right along x-axis, so as the probability values increase from 0 towards 1, you would see up to 0 to 0.5. So 0.5 this particular logit value becomes 0. That is because this particular expression is for log p divided by 1 minus p. So p divided by 1 minus p will be 1 for value of p when value of p is 0.5. So therefore log of 1 is going to be 0. So therefore at this probability value p equal to 0.5, this particular logit function is 0, right? And you can see from when the probability values are near to close to 0, then the logit values are closer to minus infinite. They are high values in the negative side. And as we increase values from 0 to 1, from 0.5 to 1, the logit values keeps on increasing, and as we approach 1, we consider values close to 1, then the logit values they approach infinite. So the range for logit is minus infinite to infinite, and you can see the probability values range 0 to 1. From this, so this is the relationship between odds and odds logit and probability value. So from this we can understand that the standard formulation for logistic model that we just saw, once we estimate those beta values, it is always possible for us to compute the corresponding probability value from a logit value. So with this we'll do one exercise in R. So the data set for a logit model that we are going to develop is this particular data set we are going to use promotional offer. So this particular data set we have used in previous technique as well, classification and regression trees. So what we are going to do is we are already familiar with the data set and variables. What we will do, we will first start with building a simple logistic model, just like simple linear regression, where we just regress outcome variable with one particular predictor. So in this particular case, the promotional offer will build a model between promotional offer and income variable. So let's first load this package x. Let's import the data set. So promotional offers data set that we have already seen in previous lecture, previous technique, and other lectures as well. So we have 5,000 observations, and this is about we can build a classification model of wherein a particular customer or individual, whether they are going to accept or reject a promotional offer. So now using logistic regression we will try and build a classification model. So you can see that data set is now imported in our environment. So let's look at the apply structure function. So we can see these variables: income, spending, promotional offer. So first we would like to start building simple logistic logistic regression model between promotional offers and income being the predictor and promotional offer being the outcome variable. Other variables also we are familiar with: age, pin code, experience, family size, education, and online. So first let's take a backup of this particular data frame. Now in this particular logistic regression exercise we would not like to include pin code, because as we have understood, too many categories we will have to deal with this. So as of now we will not like to consider for logistic regression this particular variable. So let's make that change in data frame. Now two variables, promotional offer, that is our outcome variable, let's make it factor variable, and also the online, that is the whether the particular customer is online active or not. So let's change these two variables. Now let's look at the structure. Now all the variables are in the appropriate format, variable type, income, spending, numeric, and then promotional offer is factor, then age and experience and family size, they are numeric, then education and online, so they are factor. So as we have been doing in other techniques as well, first let's start with partitioning. So we'll go for 60% observation in training partition and 40% observation in test partition. So 60-40 that is the proportion we'll go for. So let's create the partitioning. Now to build the model, so as we said, we'll just build a model between these two variables, promotional offer and income, just a single predictor. So GLM is the function that is used to build logistic regression model. So GLM first in GLM function, first we'll have to pass the formula for our model, that is promotional offer tilde income, and then second argument is about the family that we have to pick. Family is actually about telling this particular function that we would like to build logistic regression model. So you can see family binomial, so logistic is part of the binomial family. So link you can see logit, so we would like to build logit model, and the data is that training partition. So let's run this code and build logistic model. Let's look at the summary. So in the summary you would see that we have an intercept term, we have income term, estimate for these two. So beta 0 and beta 1 for income that we can see, and we can see both of these estimates are significant, right. So beta 1 for income, that is also significant here, as you can see. Now if we want to express this in terms of final model, then we would have to extract these beta 0 and beta 1 values. So this is how we can extract. So model object that we have just created, it will have this attribute coefficient, and within the coefficient we will have just two values. So we can extract using in this fashion. Unnamed function would just remove the names for this particular attribute, this particular coefficient attribute. So we are not interested in the name, so we just are interested in extracting the values so that we can write our formulation of final model of logistic regression. So let's execute these two commands. So the fitted model we can write in this fashion: probability of a particular observation, accepting a particular individual, accepting particular customer, accepting promotional offer, given their income level as X, can be expressed in this form: E1 divided by 1 plus e to the power minus b0 plus b1 into X. So this particular expression, one single predictor model, fitted model, can be expressed in this form. If you want, we can plot this. So let's look at the range of income variable and create a plot. So the plot is between income variable, that is the predictor in this case, and the promotional offer that is the outcome variable. So let's create this plot. So we would see that now let's add the this curve as well, this curve that the model that we have just fitted. So you can see, using the curve function we can express the same model here, and then we can add it to the plot. So this is the plot for our logistic response model, and all the dots that you see, these are our observations, right. And so this is our fitted model here. So as you can see, income values, they range from 0 to 50 for that this is the scale, and promotional offer, that is nothing but the probabilities value 0 to 1. So at this point we will stop here, and more on logistic regression and this particular plot as well we will discuss in the next lecture. Thank you.